This is a biomechanical analysis of a sprint start by Abbee Gosley-Fuller. A sprint start is a starting position sprinters utilize to assist them in generating a powerful takeoff, enabling them to rapidly attain and sustain their peak velocity throughout the race. The biomechanical goal of the skill is to produce maximal horizontal acceleration out of the blocks from a stationary position in order to decrease sprint time. Several biomechanical principles within the three phases of a sprint start must be adhered to determine the success of achieving the biomechanical goal. The set phase of a sprint is the initial body positioning in the blocks and the greatest determinant of the success of a sprint. The positioning of the sprinter's center of mass is important as it impacts the amount of ground reaction force that can be applied to the blocks, and thus acceleration. A study by Shindo and colleagues revealed that body mass should be evenly distributed between the feet, knees, and hands in this position to enable the sprinter's center of mass to be placed further forwards, decreasing displacement and increasing velocity out of the blocks. The second phase is the block clearance phase, where the goal is to produce the most amount of force possible in the shortest amount of time. Horizontal impulse is the major biomechanical principle that will influence horizontal acceleration and horizontal velocity of the center of mass. The final phase is the stance phase, which is where the first point of contact occurs. Here, center of mass is important in allowing ground reaction forces to be applied in a horizontal direction, ultimately impacting horizontal impulse, horizontal acceleration, and horizontal velocity. These biomechanical principles are embedded within critical features of this skill, which are specific body positions that influence the execution of the skill. The qualitative features to be analysed in the set phase include interblock foot positioning, head alignment with the trunk, and shoulders over hands, facilitating a forward trunk lean. The quantitative features to be analysed include hip flexion in the set phase, horizontal velocity, horizontal acceleration, ground reaction force and time, and force production in the block clearance phase. These critical features can be seen highlighted in blue and red on the deterministic model for the skill. In order to observe the skill and capture the essential body positions of the set phase and block clearance phase to effectively analyze the critical features, the skill needed to be recorded. Video capturing was completed using an iPad with slow motion capabilities, recording at a frame rate of 120 frames per second. This allowed for frame-by-frame playback to define and analyze critical moments of the movement. This was recorded from a sagittal view, being filmed at a right angle. The participant completed 3 maximal effort trials to account for error in an outdoor setting to ensure sufficient lighting whilst avoiding direct light and glares. A 1-meter ruler was used for collaboration at the beginning of each take, and colourful reflective markers contrasting the participant's clothing were placed on the relative anatomical landmarks of the participant, being the talocrural joint, the lateral side of the patella, greater trochanter, acromial, and the radial ulnar joint. Dark clothing was worn to contrast the participant from the background and to increase the visibility of the markers. Prior to recording the skill, the participant was guided on how to perform the skill correctly through the use of visual models where feedback was provided to improve their performance. Knee flexion in the set phase is a critical feature impacting center of mass and ground reaction force, and is important in facilitating other optimal body positions, ideal for achieving maximal horizontal acceleration. A study by Genowiski and colleagues shows that rear knee flexion is optimal between 90 and 130 degrees. However, a study by Milanese and colleagues identified that greater rear knee flexion results in better sprint performance. The study compared kinematic parameters when knee flexion was at 90, 115, and 135 degrees respectively. Results showed that 90 degrees of rear knee flexion achieved greater horizontal block velocity and force impulse due to increased horizontal force production at the takeoff, resulting in greater acceleration and thus rapid attainment of peak velocity. Anything less than 90 degrees, however, will not allow for the hips to be placed high enough for the center of mass to be optimally positioned for an explosive takeoff. As seen here, the rear knee flexion of the participant was measured from the hip to ankle joint, as done in the stated study above, and was recorded at 131.3 degrees. In regards to correcting this performance, Lee and colleagues and Milanese and colleagues suggest that positioning the blocks closer together will decrease knee angle, allowing for the hands to be placed further forwards, facilitating a forward trunk lean and lower center of mass, producing horizontal direction, ultimately decreasing displacement and increasing velocity. According to Siasi and colleagues, elite sprinters leave the blocks at a velocity of 3.33 meters per second on average. Velocity was calculated using the formula velocity equals change in displacement divided by change in time, where the initial change in displacement and time was 0. Using the horizontal displacement of the center of mass of 50.51 centimeters and the time of 0.37 seconds, the average velocity was calculated to be 1.365 meters per second. Horizontal acceleration was then calculated using the formula final minus initial horizontal velocity divided by the time taken to travel that distance. As the initial velocity was 0 and the horizontal velocity at the push phase was 3.33 meters per second, this was then divided by 0.37 seconds to equal 9 meters per second squared. Ground reaction force was then also calculated using the formula of ground reaction force equals mass times acceleration, where the mass of the participant was 68 kilograms and the acceleration was 9 meters per second squared, resulting in the ground reaction force to be 612 newtons. From here, the horizontal impulse could then be calculated, which was using the product of the ground reaction force, being 612 newtons, divided by the time in contact with the blocks, which was 0.37 seconds. This gave us the value of 226.44 newtons per second. Horizontal velocity can be corrected by positioning the center of mass further forwards and closer to the ground, which can be achieved by placing the hips above the shoulders and ensuring the rear knee angle is between 90 and 130 degrees of flexion. Placing the center of mass in front of the sprinter causes a change in the direction of force application and a change in direction of impulse to a more horizontal direction, whereby greater force production can occur, meaning the sprinter will leave the blocks at a greater velocity, decreasing sprint time. The results of the participants show that their rate of force development is a weakness to their overall sprint performance. According to Slowinski and colleagues, the ground reaction force of an elite male sprinter is on average 1,028.2 newtons, significantly higher than that of the participant. Correcting their horizontal ground reaction force during the block clearance phase will maximize acceleration out of the blocks, which can be done by adjusting the block positioning and body angles. Additionally, the impulse of the elite male sprinter on average is 276.2 newtons per second as a result of greater block contact time. If the participant increased their block contact time during this phase, this would improve their impulse for greater acceleration. For the qualitative features, it can be seen that the participant's feet are not properly positioned in the blocks during the set phase. This increases energy loss and minimizes propulsive forces during the takeoff, decreasing the velocity of the sprint. The feet should be placed fully on the blocks so optimal plantar flexion can occur, as this positions the body parallel to the ground and places the center of mass further forwards, so that the force generated propels the sprinter in a horizontal direction, maximizing acceleration out of the blocks. Head alignment with the trunk is another critical feature that optimally positions the body for maximal acceleration out of the blocks. In addition to placing the center of mass where it enhances force production, when the head is neutral and in line with the trunk, it provides increased efficiency by reducing muscular tension of the upper body, generating a powerful takeoff. To correct foot positioning in the blocks, ensure the blocks are ergonomically positioned for the sprinter in relation to the starting line. Placing the hands up to the line will ensure that the hips can be held high and that the shoulders can be placed forwards over the line, optimally positioning the center of mass for increased velocity during the sprint. To correct the head alignment, the head should be tilted downwards to where the eyes meet the starting line, forming a straight line with the trunk. This will increase energy efficiency and stability during the takeoff, producing optimal horizontal impulse that will propel the sprinter forwards. As shown here, the participant's shoulders are positioning behind her hands, placing her center of mass further back and in the direction of the orange line, which increases displacement, making it harder to achieve an explosive takeoff, and also increasing sprint time. The participant can correct this by placing her hands wider than shoulder width in front of the base of support and closer to the starting line, which will naturally create greater trunk flexion. This body position is essential for sprinters to have an explosive takeoff, as it generates optimal propulsion forces and increases stability in order to achieve maximal acceleration and reduced sprint time. Thank you for listening, and here are a list of the references used.